to introduce again Justin McInroy for this is your fourth part.
My fifth part, the final part.
Fifth part of his nice course about axial algebras. So, Justin, the word is with you.
Thank you very much. So last time we were talking about ideals. So this time my plan is to very quickly sort of finish that off and then discuss a number of different topics which are going to be discussed a lot more briefly, so much less detail, but I'd like to give you an overview of some different areas in axial algebras, some research directions, some quite new research results, and some open questions. Okay, so last time, if you remember, we were studying ideals and we split them into two classes, those which didn't contain any axes and those which did contain some axes. And the first type, we were thinking about the first type first, and we showed that there was this unique largest ideal called the radical, which didn't contain any axes. And in this important theorem at the end, we showed, or I stated, that the radical of the algebra is equal to the radical of the Frobenius form, if and only if the Frobenius form is non-zero on the axes. So I sort of indicated that I would give you a proof of this, but I've got quite a lot of material to get through, and the proof is in the notes. So I'm just going to say here that the proof, again, uses that induction on the length of products. So if you remember one of our previous proofs, we, with the Frobenius form, we had an element W and we split it up into W1 times W2, where those were both, where W was taken to be a product of axes, and we can split it up into a smaller product of axes. So all I'm going to say for the proof, just give a very much a hint, is just say that this is by induction on the length of a product of axes. So this I can't even write proof here, proof hint. But as I say, the full proof is in the notes. So, yeah, let me just make a brief comment on this, which is to say that, so I said last time that this is very useful because it allows us to easily calculate what the radical is. And so this is why it's an important result, particularly if the radical is trivial, then this will show that it's trivial very easily, or perhaps it's very small. But it's actually not the full answer, or not the full situation, because suppose the radical is very large. However, if the radical is very large, then if the radical is very large, then it might still be difficult to calculate all of the ideals which are contained in the radical. We can calculate the radical easily, but there may be many different ideals which are contained in it. So we're back to our old problem there. And so sometimes even we have examples where this radical is codimension 1 in the algebra. So when the radical is codimension 1, and actually we're going to see, or I will at least mention one of these later in the lecture, the so-called high water algebra. And also there are some other ones in some family of examples described by Yabe, which I'll also mention. But actually this one is the most difficult case to date, and we'll see why in a bit. Okay, so, all right, well, I've given an exercise in the notes, so I'll write that here. Our running example of the Matsuo algebra. So find the radical for the Matsuo algebra so the one I mentioned earlier, our sort of running example, which is the one for the group S3. So find this for all values of eta. So that will be a good exercise to do. So, okay, that concludes what I wanted to say about ideals which are contained in the radical, those which don't have any axes. Let me quickly say something about ideals which do contain axes. And I just want to recall a technique we used before. Suppose I've got two axes, I can write A as a sum of some A lambdas, where A lambda is in the lambda eigenspace with respect to B. So I'm decomposing A with respect to B. And as we noted before, we have this projection map. So if A is primitive, we have a projection map. Actually, this is going to be from all of A onto F, which is just given by A1 equals phi B of A of B. So that's how you get the value there, if you remember. And I want to form a graph from this. So let A be a primitive algebra. The projection graph is the graph with vertices the set of axes and a directed edge A to B if, we get this the right way around, the projection of A onto B is non-zero. So this is just recording when we have a non-zero projection of one axis onto another. And the lemma is this. Actually, do I need to give you, I might need to give you just a little definition first. If we've got a directed graph, we can, somebody is requesting remote control of my screen. Oh. Probably accidentally. Yeah, so if we have a directed graph, then we can consider the outset of some subset of vertices. And all I mean by that is the set of vertices which I can reach from that particular set. So let me just say that the outset out of a graph and some subset of vertices is the set of vertices reachable by a directed path from Y, from some element of Y. Okay, and I think I need a new page for this. So with that in mind, we can prove the following lemma, which says, again, let A be, I'm just going to write primitive, it's primitive axial algebra. Oh. I've got some odd red lines on my screen which I'm showing, but they don't show up on my thing. That's very odd. Okay, so let A be a primitive axial algebra, and gamma its projection graph. If Y is a set of axes contained in an ideal I, then the outset in gamma of Y is also contained in my ideal. So what this is doing is saying that if you've got some axes which are in your ideal, what other axes are in your ideal? Well, we can find these by just using the out graph, or using this projection graph and looking at the outset. And again, I'm running quite short on time, so I'm not going to give you a proof of this. It's in the notes. I guess I will just skip down to my last lemma here, which again says that everything from above, if in addition I have a Frobenius form, and suppose that the form is non-zero on two axes, A and B, then the following are equivalent. So one, the form on the axes is non-zero. Two, there is a directed edge A to B, and three, there exists a directed edge B to A. So what this is telling you, this is a very easy proof for this. You should be able to see this immediately from that lemma we had last time on values in the form and the projection. And what this is telling us is that when we have a Frobenius form, this projection graph can actually be considered as an undirected graph. And finally here, I guess I'm going to give a corollary which says, suppose the above with the Frobenius form. So suppose the above, sorry, this is very shorthand here. Suppose the above such that it is non-zero for all axes. If the projection graph is connected then all ideals are contained in the radical. I.e., there are no proper ideals, I should say, all proper ideals are contained in the radical. That is, there are no proper ideals which do contain axes. So that's an easy corollary from this lemma. Okay, so that is all I wanted to say about ideals. Let me now switch and do some slides. New share. So what was this? Like that. Excellent. Good. So I wanted to say, as I said, some more recent research and problems. So it's going to be a very quick trip through this. So this is just a recap of what we've covered already. And yeah, I'm going to discuss some more things. So the first one of these is sum decompositions. So yeah, most of the results from this section are taken from this paper with Sanhan Khazra and Sergei Shpectorov. So you might think that if our definition of a radical is a good one, then maybe modulo this radical, axial algebras are sort of semi-simple. They look like a direct sum of simple algebras, say. And so it's sort of natural to consider some decompositions of algebras. So for us, I just want to think about the situation where we have our algebra, which is generated by a set of pairwise annihilating subalgebras. Then, in fact, this is exactly a sort of sum decomposition as a vector space. And I'm going to write this as this box product here. So this nice boxiness. And I'm going to say it has a sum decomposition when we have this property that it's generated by pairwise annihilating subalgebras. And notice this is over some index set. I am allowing this to be infinite, so if you want. And yes, the standard thing will happen with direct sums with the annihilator. But what I want to concentrate on is this. So in this definition we had, I didn't require these AIs to be axial subalgebras. I just said they were subalgebras. So what would be really nice is if some decompositions respected the axial structure. And so we've got this theorem which says the following. So suppose we've got a primitive axial algebra which is a sum decomposition. And I want to consider those axes which are contained in the AI. So I'm going to split up my axes into these xi's, which are those axes which are contained in the subalgebra AI. And I'm going to consider the axial subalgebra, which is generated by those axes. What does the theorem say? Well, firstly, this splitting up of these axes really does partition the set, i.e. every single one of these axes is in one of these, and moreover, it's in exactly one. And secondly, the algebra is some decomposition of axial subalgebras. So these AIs these BIs might not be exactly the same algebras as these AIs, but we still get some decomposition. So in some sense, some decompositions do respect the axial structure. So now you might ask, well, I've got these sum decompositions. What's the best sum decomposition I can get? So maybe a better way to say that question is there a unique finest sum decomposition? So can I keep on splitting up my sum decomposition into finer and finer sum decompositions such that I get down to a final one, and that moreover, that one is unique? So suppose we've got two subalgebras which annihilate each other. Then in particular, their axes must annihilate each other as well. And what I'm going to define is another graph called the non-annihilating graph. And this has, again, vertex set, the set of axes, and there is an edge between two axes if and only if they don't annihilate each other. And okay, so what's this going to say to us? Well, it's clear that the xi must be a union of connected components in this graph, because different xi's annihilate each other, as we saw up here. Xi, xj is 0. So that means that these lie in different connected components, and they must actually be full. So any two axes which don't annihilate each other lie in the same component. So the xi's are a union of connected components. And so the conjecture is that actually the finest sum decomposition is given exactly by the connected components of the graph. So yeah, that is just exactly what I said here. So what progress have we made to this? So let's think about what happens on the level of groups first. And for groups, we have the following. So suppose we've got this sum decomposition, then I've changed notation here. I'm so sorry. This is the Miyamoto group. I'll correct this. This is also on my website. I'll correct these slides later. So the Miyamoto group is a central product of the Miyamoto groups, which are generated by just these connected components. So actually, this is sort of the best we could hope for, a central product, because these things are going to commute, but they may have a center which is common to each. So a central product is the best we could hope for. So that's good. The groups sort of work as expected. So what about for the algebra? Well, for the algebra, it turns out it's a lot more difficult. And I need to define a new concept called a quasi-ideal. So I'm going to say that some subspace of my algebra is a quasi-ideal if it's invariant under multiplication, not by all of the algebra, but just by the axes. And I'm going to say that the spine of the algebra is the quasi-ideal which is generated by the set of axes. And finally, I'm going to say that the algebra is slender if it's equal to its spine. So if you like, there's no meat on the bones. So exactly that, if the algebra is exactly its spine. So I just want to give you a bit more of a picture. So the spine will contain elements such like, so it contains all the axes. It also contains all products of axes. And it contains things where I just keep on multiplying this product by a new element. So I have C times D, I multiply it by B, then I multiply it by A, and so on. But it doesn't necessarily contain elements like this. So if I have C times D and A times B, and I multiply them, that's not necessarily in the spine, unless, of course, I can rewrite it as a sum of things which look like this. Okay, so hopefully that gives you a little bit of an idea of what the spine looks like. And it turns out, okay, I've got this aside which says that basically an algebra is M closed for some M if it's spanned by products of length at most M in the axes. And so in particular, if you only get up to length 3, then all elements here are of this form. So every 3 closed algebra is slender. And we only know of a handful of examples which are 4 closed or more. And the largest one is 5 closed. So what I'm trying to argue is that this property of being slender, it's not that much of a restriction, at least that we know of at the moment. And okay, I was going to introduce this several lectures ago, but I decided against it actually. So fusion law is called Shpectorov if we have 0 in our fusion law, and if 0 times all of the other eigenvalues is contained in that eigenvalue, a subset of that eigenvalue. And in particular, all the fusion laws I've shown you are Shpectorov. And okay, our partial result for that, remember our conjecture that we want to prove, our partial result is the following. So suppose that we have a Shpectorov fusion law, then the conjecture holds if at most one of these AIs, that is the subalgebra generated by this connected component here, if at most one of these is not slender. So obviously we'd like to remove this slender requirement, we'd like to remove this Shpectorov fusion law, but I think anyway that this theorem answers that conjecture in a lot of cases, the vast majority of cases, I think. Okay, so what do I have next? All right, so what we want to do, so I'm moving on to a different topic now. So all the way through, what I wanted to do is classify axial algebras, and maybe one way of going about that is to classify the algebras which have a given fusion law. And okay, if you remember, here are some of the fusion laws. So this one, remember we saw, this is what the 2B, that small 2-dimensional one satisfied. And then this is the Jordan type one, and this is the monster type one. And so let's just consider the smallest one first. So this most simple fusion law is, as I say, the one which was satisfied by this 2-dimensional algebra, which I call 2B. And it turns out that we can do better than this. If we've got a primitive axial algebra, then every associative primitive axial algebra satisfies this fusion law. And conversely, every axial algebra with this fusion law is associative. So I actually call this fusion law A because it's the associative fusion law. And I guess this is exactly what you'd think of if you think of an associative algebra. Every idempotent has eigenvalues 0 and 1, and that's what we're seeing here. Okay, so what about the next type of fusion law, this Jordan type eta? Well, we've seen already that this class of algebras, these Matsuo algebras, which are defined from a 3 transposition group. So this was an example in my second lecture, I think, was motivated in my first lecture. The claim was that these are axial algebras of Jordan type eta, and that was actually one of the exercises for you. And actually, there was this theorem by Hall, Rehren, and Shpectorov, which says that every primitive axial algebra of Jordan type eta, where eta is not equal to a half, is one of these Matsuo algebras. Okay, but what about the case where eta is a half? So if you'll remember, in the first lecture, I said that most Jordan algebras, actually this most here means exactly those Jordan algebras which are generated by their idempotents. So most Jordan algebras are axial algebras of Jordan type a half. And the conjecture is that every axial algebra of Jordan type a half is, well, maybe a quotient, but it is a Matsuo algebra or one of these Jordan algebras. And yeah, this is a conjecture since that first paper where that initial result was proved by Hall, Rehren, and Shpectorov. And I just want to think about how they originally proved that. So the proof for that was first proved by considering the 2 generated case. And the 2 generated algebras for Jordan type a half are known. They are just so-called spin factor algebras. Actually, there's one additional one, which is sort of a nil cover of a spin factor algebra, but morally it's just the spin factor algebras. And in a very recent result, Gorshkov and Straletov have recently determined the universal 3 generated algebra of Jordan type a half, primitive algebra of Jordan type a half. So they've done not just 2 generated, now we know 3 generated. However, at the 3 generated level, every Jordan algebra, which is 3 generated, turns out also to be a Matsuo algebra, i.e. the 2 classes at that 3 generated level are indistinguishable. And this is a result by Tom Demetz and Felix Rehren, and there's a correction in a subsequent paper by Takahiro Yabe. And okay, but for 4 generated algebras, those classes really do diverge. So you get Jordan algebras, which are not Matsuo algebras. So if you could prove it for the 4 generated case, you could probably, exactly the same techniques would prove it for all Jordan algebras, or for all Jordan type algebras of a half, Jordan type a half algebras. And actually, so Gorshkov and Straletov have some new ideas in their paper, and there's a group of us who've planned a workshop to try to use some of these new ideas to attack this problem. It's been slightly delayed by COVID, this workshop, as have all these things, but hopefully this will be going ahead soon or early in the new year. Okay, so what about the next type of, fusion law? So I want to think specifically for monster type 1/4(1/32). So this is the fusion law which the Griess algebra specifically satisfies. So we'd like to be able to classify all the axial algebras of monster type, actually for monster type alpha beta. But even in this case here, for 1/4(1/32), this seems very hard. I don't think we really have any good ideas for how to attack this. but we do know some results for two generated algebras. And if you remember in the Jordan type case, I argued that this was how the proof went. We did two generated, and then we sort of stepped up from there by gluing together. I'll say more about that in a bit, by gluing together two generated algebras. And for a long time, since 2015, we've had this Norton-Sakuma theorem. So this is a generalization of a theorem which was known for VOAs, for vertex operator algebras. It was known for the Griess algebra. Then it was known for Majorana algebras. Then it was generalized to axial algebras. And I think now this characteristic 0-bit can be got rid of, and also the Frobenius form. I think in a very recent result, maybe last year, this can now be got rid of as well. But certainly the result from 2015 said that the two generated axial algebras of monster type a quarter 1/32, in this case, then the two generated algebras are one of the following 9 types. And I've listed 9 things here. So I don't expect these labels to mean much to you. They're known as Norton-Sakuma algebras because originally, so Norton was the person who discovered them in the Griess algebra, and Sakuma, I think, proved this in the VOA case. So they're known as Norton-Sakuma algebras. And I sort of argued before, so these names come from conjugacy classes in the monster. So my comment, I guess, a couple of lectures ago about where 2B came from. Exactly the same thing for all these. Anyway, there are 9 algebras. And it turns out these Norton-Sakuma algebras are precisely the two generated algebras which are found in the Griess algebra. So in particular, if we've got some axial algebra, which has nothing to do with the monster and the Griess algebra, this should say not contained in the Griess algebra. So even if it has nothing to do with the Griess algebra, still these Norton-Sakuma algebras are the only possible two generated algebras. So that's I think, a rather odd happening. Okay, let me give you something of an idea of what these numbers are for. So these numbers represent the order of the product of the Miyamoto involutions. So these algebras are two generated. You take the two generators, you look at the Miyamoto involutions, and you multiply them, and that is some group element, and the order of the product is the number. So the orders were 1, 2, 3, 4, 5, and 6. And it turns out, so Sasha Ivanov has made this straight flush conjecture, which says basically that if you've got an algebra where you see all of the products, so all the numbers here, 2, 3, 4, 5, and 6, 1 always occurs. So if you see 2, 3, 4, 5, and 6 in some two generated subalgebra, then you must in fact embed into the Griess algebra. So this is an open conjecture. So what about for the alpha beta case? So Felix Rehren generalized these Norton-Sakuma algebras for the alpha beta fusion law. And okay, so I've written some of these here. You'll notice the same start, and now I've written in some things afterwards. This is meant to be what the value of alpha and beta here is. So in this first one, any alpha and beta give you, or almost any alpha and beta give you, an algebra. In this second one, alpha has to be a quarter, but you're allowed any value of beta, and so on here. So you'll notice that, well, firstly, also all Jordan type algebras are examples. So remember we said before, Jordan type algebras are examples of monster type algebras because the fusion law is contained in the other. And this 2A example is actually a Matsuo algebra with eta being a quarter. Our our favorite running example with the group S3. And the 3C algebra is exactly 3C of 1 over 32. But what I wanted to say, what I was saying here is that these families of examples up here don't exist for every value of alpha beta. Some only exist for a subvariety. So this one here only exists where alpha is a quarter. But the amazing thing is, if you plot all of these varieties, so all of these varieties here, where these exist, these varieties intersect in a unique point, and that unique point is a quarter 1 over 32. So we have no idea why this should be true, but it seems to somehow point to the unique nature of the monster. So I think we'd very much like to understand this. Okay, so that was Felix Rehren generalizing some of these families that we saw. But in a recent result by Yabe, he's classified all of the 2-generated algebras which occur. But he had to do it under this initial, under an additional assumption, which is a symmetry assumption, saying that there is some automorphism of the algebra which switches the 2 generators. So, by the way, I should say, all of those previous examples, they all have this symmetry assumption. So, okay, sorry, the previous results did not assume that symmetry assumption. However, they are all symmetric. They all have such an automorphism. And so this is a theorem by Yabe last year. There's a very tiny bit added by Clara Franchi and Mario Mayanardis. So suppose you've got one of these symmetric, i.e. with this automorphism, axial algebras, oh, this should say 2-generated in here as well, 2-generated axial algebra, then you're one of the following. You are either an axial algebra of Jordan type, alpha or beta, or you're a quotient of this high water algebra. So I briefly mentioned that earlier when I was talking about ideals. I will say a bit more about this in a minute. You're a quotient of this high water algebra, or the bit which Clara and Mario found was that this high water algebra has a characteristic 5 cover. And here, for both of these, you must have alpha and beta being 2.5. So alpha's 2, beta's 1/2. Or you're one of a list of examples. So what Yabe did was he proved this theorem basically, not for characteristic 5, but for all other characteristics, he proved this. And characteristic so not 2, because we have no gradings, and not 5, but 5 was done by Clara and Mario. He found all these additional algebras here. So you notice some of Felix's algebras, Felix Rehen's are here, 6A and 5A. So these ones here. So he found some additional algebras, which I've labeled by this Y for the ones he found, and also these. So by the way, this is my notation for these. This isn't the notation he's used, but I like to stick to this notation because this number indicates the number. So that number we had before, the order of the product, it is also the number of axes which are in these algebras. So in this closed set of axes in these algebras. This J here is Vijay Joshi. So he found these in his PhD thesis. He introduced a sort of a doubling construction for the Matsuo algebras, which produces so-called double axes and produces these algebras. But actually Yabe sort of rediscovered these. I don't think he knew, or he didn't recognize these as such. This I here means infinite. So normally these two algebras normally have infinitely many axes. However, for certain values of the parameters, they may have finitely many. And Sergei Shpectorov and I, in a recent paper, showed exactly when what the number of axes here are and when they have them. So anyway, most of this, almost all of this result is due to Yabe. It's a very, was an unexpected result last year, very powerful result. So what I wanted to say about the high water algebra, so all of these algebras on here are finite dimensional algebras, apart from the high water algebra, which is infinite dimensional. It also has infinitely many axes. And when these were found, these were a big surprise. Yeah, so this is Clara Mario with the cover. And the big problem, so my link to earlier with the ideals, is that here, the radical is codimension 1, and even worse, it's codimension 1 in an infinite dimensional algebra. So finding all the ideals here is, is very difficult. And so I've been working with Clara Franchi and Mario Mayanardis to do this. And we're currently writing it up, which is the question mark here. But I think we've basically found all the ideals here. And the surprise is that for every number, every natural number, there is a quotient with that number of axes. So we have examples where we have that number of axes in all of our. So both here we can have a two-generated axial algebra with any number of axes in a closed set, and also turns out in these cases you can as well. So we previously to this, we thought that you could only have, well, we'd only ever seen up to 6 axes, and then suddenly we saw infinitely many, and now we have any number. So it makes it a lot richer for this alpha beta than it does for a quarter and 1/32. So what about for ones which are not symmetric, so don't have this automorphism switching the axes? Well, we've got no idea. So I'd like very much to be able to answer that question. So maybe a hint at how you might do that and how you might expand to algebras which aren't two-generated. So let's suppose we've got some axial algebra, then clearly for a pair of axes, it generates a two-generated subalgebra. And roughly speaking, very roughly speaking, we call the configuration of all these two-generated subalgebras the shape of A. So if you think about the configuration of all of these, they intersect, and somehow this forms a somewhat complicated configuration. This is going to describe quite a lot of the structure of your axial algebra A. But on the other hand, suppose you think up your favorite configuration of two-generated subalgebras. You might ask, well, is there an axial algebra which has that shape? So for those of you who know about groups and amalgams there, this is sort of like asking, I've got an amalgam of groups, I want to glue together a lot of groups. Is there a group, a completion of this amalgam which contains all of these? So just as a hint to how it's a bit more complicated than just that, if we've got conjugate, if the pair AB of axes is conjugate to the pair CD, i.e. there's some element of the automorphism group which takes A to C and B to D, then it takes the two-generated algebra on this to the two-generated algebra on these. So those two algebras must be isomorphic. So our configurations must be constrained by this. By the way, sort of as a slight aside here, Sergei Shpectorov and I have written an algorithm which does exactly this. You give it a shape and a Miyamoto group, and it will try to build the axial algebra with that given Miyamoto group and shape. So there's a computational aspect to this as well as a theoretical one. But I want to stick with the theoretical one for the minute. So just going back to this, our configurations, we need to somehow be able to talk about this without knowing that we have an axial algebra. So we need to be able to understand this without having an axial algebra. And in a paper which came out just earlier this year, sorry, on the archive just earlier this year, Sergei Shpectorov and I have introduced this concept. We call it an axet, which sort of mimics the action of a set of axes together with this tau map. So I'm associating automorphisms, and this is going to generate a group, and this group will act on the axes, but there's no axial algebra around. But what this allows us to do is talk about shapes and completions of these shapes in a rigorous manner. And let's just go back to thinking about our two-generated case. So suppose I've got a two-generated axet for a C2 graded fusion law. So these are the ones we've mostly been interested in. We showed that it falls into one of two types. So there are the regular ones. So here you've either got one orbit of axes, or you've got two orbits of axes, so one for each generator, but those two orbits are the same length. Or it's what we call a skew case, and that means there's one orbit which has size k, and the other orbit has twice that size. This is for any k. And looking at the examples that we saw before, all of those examples we saw before had regular axets. So actually, we don't know any examples with a skew axet. So these may exist, they may not exist. But if such an example does exist, so the one axis is going to be in this set of size k, the other is going to be in this set of size 2k, well, there's clearly no automorphism which switches these because they've got different size orbits. So it's necessarily it is one of these non-symmetric cases. So this would be very interesting if we could find one of these. So do they even exist, or can you show that they never exist? And I guess what I wanted to say also is that so there's this two-generated result. We've also started considering sort of shapes on larger axets, and we've got some first results on classifying all the completions for some given shapes on some three-generated axets. So that's like in the Jordan algebra case, we went to those three-generated algebras first. So we have some results on these completions, and they hold for the fusion law with alpha and beta, not just for a quarter 1/32. But I think that this is a sort of growing area of research, and there's many more results that you could think about proving here. So that's one direction to take it, trying to calculate some more of these, trying to, both in a theoretical way and a computational way. Hopefully I've hinted at some of the different areas this subject is expanding to. I haven't been able to cover them all by any aspect, but I've tried to give you an overview of some of the research areas in the last, I guess, 40 minutes or so. And over the other lectures, I've tried to give you a reasonable background to be to allow you to think about questions here and read some of the papers and so on. So I've given you some references at the end of the slides. The slides are on my website, and that's me out of time. So thank you very much.
Thank you very much, Justin. Really nice talk. You did a very good job for us.
Thank you.
Any question? Any remark? Any remark?
I think maybe one's coming.
I would ask a question. So if you compute in the classification, what mathematics software you use? For example, Maple or another software computation mathematics.
So in terms of the computational side, the algorithm which Sergei Shpectorov and I designed, I implemented in Magma, but there is another sort of earlier algorithm for doing a similar thing, which is implemented in GAP. So either of both of those are available. You can find them. They're both on GitHub. You can download them freely and use them. Yeah, and I mean, this provides you with, so you can build the algebras there, and then you can investigate some other questions computationally. So maybe some other questions you might investigate are things like, so the Miyamoto group is a subgroup of automorphisms, but can you find what the full automorphism group is of some of the algebras? Actually, in doing so, you would discover maybe some other axes which are not in an initial closed set of axes, but some new axes in your algebra. So there are various other computational questions which you might like to consider. So you could use either Magma or GAP to do that. And actually, I've got, so as part of this algorithm, I'm able to save the algebras which I construct. So I've got quite a large library of constructed examples. So if you did want examples to play with, I have saved files which would give you all the structure constants for the algebra.
Okay, thank you. So I would express great thanks from Madagascar to your 5 hours of talks. We are grateful. Thank you.
Thank you very much.
I thank you too, Justin.
Thank you. It was a wonderful call. Yes.
One more question. Of course. One more question. Let us thank again our speaker.